How's it going, guys? Hey, Devs is back, and we are back doing some more LeetCode. We're doing some more easy tree problems. We're just getting, I think last video was our first tree. We did we'll start with the binary preorder. We did the binary in-order traversal. We did the maximum depth of a binary tree, and we did the minimum depth of a binary tree. All these are pretty, fairly simple recursion problems, and then we're going to do two more traversal problems, pre-order and post-order. Those are the two other orders, and then in order as well. In order was the first one we did. So in order is kind of like something like this. Um, so like you check if it has a left node. If it doesn't, um, you see if it has a left node. If it does, you call the function again, and then the function returns a list. So you add every value this function calls, the function call returns into your list. And then the second thing you'll add to the list is the node you're at. And then you'll check the right list, and then you'll add everything in there. And we'll kind of walk through this a little bit. I'm going to go a little bit quick because we got, see that? That's a puppy. His name, not her, his name is Shadow. He is a Labradoodle, and he does not like the kennel too much. So if he starts whining, we'll get him out because we're just trying to get him used to it. So he's been in there a good bit. And then the way you start this problem is you create a list of integers, and I've just called it list, and then this is going to be equal to a new linked list of integers, and be sure to always call the constructor when you create an object. And from there, we want to see if the root is null. So if the root equals null, we'll return the list with nothing in it. Because in example 3, it returns nothing. So this is problem 144. Given the root of a binary tree, return the preorder traversal of its node values. Um, oh, I think, was it our last video? Not unresponded. Okay. So day 15. We got a comment on one of the videos asking, yeah, can you solve the end queen problem, please, so I can understand your approach, as I find it very difficult. Recursion is not my thing. I feel like after doing it, I feel like I am dumb and I'm not capable for job after solving a recursion problem. Yeah, of course, we can do this. So I haven't even taken a look at this problem. End queens. Given the end queens puzzle. Ooh. I'm placing end queens on an invite. N by N chessboard such that no two queens attack each other. Given enter in, return all distinct solution of N queens puzzles. We return the answer in any orders. Yeah, we might. We might take a look at this problem later. But I just think today we're going to be working on three problems. Which also deals with recursion. We're going to incrementally make our way up. A lot of binary tree problems can be solved with recursion. I really don't know how to solve binary tree functions without recursion. So we'll go ahead and start with the pre-order traversal. So pre-order would be, yeah. So we want to add the nodes value, and then we want to add everything in the left value. So you see it goes, we're given the root node and wants us to add this into the list. And then when we go to 2, we'll check the left side first. We get to the 2 node, then we add it into the list. Then we check its left side as well. 4, we add it into the list. And then we go back to 2 after this function call iterates, and then 2 will check its right side, and then it will add 5 into the list, and then 5 will check its left, add 6 into the list, and then 5 will go back to 5, 5 will check its 7, so add 7 into the list, and then After that, it will return the function, return the function, return the function. Go all the way back to 1, and then 1 will go to its right side, add 3 into the list. 3 will check its left, there's nothing on the left. So then it'll check its right, and then it will add 8 into the list. And then it'll check its left, go to 9. And then 8 will check its right, there's nothing in the right, so then it returns to this section as the lifts. And we'll kind of walk through this just a little bit. I'm not going to do too much explaining because I do have like I said, brand new puppy. He is napping. He was whining when we put him in there, but I'm glad he is not whining now, so we can solve a little bit of LeetCode. So for in order traversal, the first thing we want to do is add the current node into the list, right? So we'll do list.add the root.vows, right? And then we want to see if root.left does not equal null. And if it doesn't equal null, well, we don't even need the curly braces because it's one statement. If it doesn't equal null, we can do list.add all because it's going to be returning a collection. Add all adds everything in the collection into the list. So we'll do list.add all and we'll call the function and pass it the root.left node. Okay, and then next we want to check the right node. Right, does not equal null. And then we'll do this dot add all preorder traversal. And then we will pass it the root dot right node. And then at the end, we want to return the list. So all this is doing is we created a list. If the list is root is equal to null, then we just return the list. Else we'll go ahead and add the root value. And then we'll check if it has a left root, and if it does, we'll go ahead and call this function again for that subtree. So you can imagine if we go to 2, 2 is a tree as well. So we want to do in order traversal for it, or pre-order traversal. And then from there we'll call it left again. And we'll do that all the way down. Well, technically I don't even know if we need the if statements. Because we already checked if the root is null. Yeah, so that runs for all the cases, and then we go ahead and submit this. That should work. There it goes. So the only difference between in order, post order, and pre-order is where you put this list.add, right? So if you see, I think I did my in order a bit different. Yeah. So we can like I just stated, we can remove these if statements. Since when we pass it a null of root, or a node, like a null node, it will go ahead and return an empty list. And then we can pre-order. We link a new tab. So if we submit this should work as well. And the only difference is where you put the list.add. We always check the left first and then the right. And then the list.add, it comes first for pre-order. And then it comes the middle for in order. And then post order, you can imagine you do the list.add in the last section. So we can go ahead and do list integer list. This is equal to new length list integer, and then call the constructor, of course. So then we want to see if the root is equal to null. If that's the case, we return the empty list. And if not, we want to list.add all, everything in the post order, so with the root dot left node. And then we'll do the same for the right node. Post order traversal root right, and then we add the current value at the very end, root dot value, and then from there we return the list. And this should work for the post order. Post, oh, I capitalized the O in order. It's not capitalized. If we run that, it should be correct for all the test cases. There it goes. And then if we submit it, it should, be fine. These are all easy problems because this is just binary traversal, right? So we just return the node or the value itself. That's not too bad. Yeah. So, like I said, the only difference is when you add the value itself. So this one adds 1 initially, and then pre-order adds it initially. Post order will add it after the left tree has been added. So post order, it will go all the way to the left and add the 4. Then after the left node exhausts and it returns back to 2, then it will add the 2. And then it will check its right node. And then the right node checks its 2, and then it'll be 6, and then it'll be 5, and then once it gets back to the 5, it checks its 7, or its right node, and then that goes all the way back to 1, and then 1 is finally added. And that would be the pre-order. And then this is easier to see with binary search trees. I don't know why they didn't give you binary search trees for these problems. Because if you're doing in order, or if you're doing post order for binary search trees, it would give you the so pre-order, and in order would give you the actual in order values, right? So, or like a binary search tree is, its kind of rule for it, the way that it adds nodes is given the head, everything to the left on the left side of a node, it has to be less than the node's value, and everything to the right side of the node has to be greater than the node's value. And that's how it builds the tree. So, say you're looking for 4, so then 4 it has to be on the left. And then say, if this was 5, then 4 would have to be on the left. And then if this was 4, then you'd find 4. But if this was 5, and then this was 4, and this was 3, then you would go 5, then 4, then 3. Like 3 would have to be to the left of those because it's less than those. But we'll probably do some binary search trees in the next episode. I just want to get a little bit more easy problems because I've been dealing with the puppy. I got to take the puppy out one more time because it ate around 7, but it hasn't pissed or shit. Well, it shit as soon as we got in here, but it hasn't shit again. So, it ate around 7, so that was 2.5 hours ago. And puppies usually shit within 10 minutes of eating. So, we're gonna take her out one more time, or him, not her. I keep on saying her. We're gonna take him out one more time and see if he poops. But I think tomorrow the problem we're gonna do is the. Let me take a look. Count complex. We might do the add and remove problems. Delete node and binary search tree. Yeah. So these are fairly simple operations. Like in this binary search tree, we know that if the starting value is 5, then we know if we want to look for 2, then 2 is less than 5, so we go left. and then 2 is less than 3, then we go left. And then 2 is here. And then for some reason, if we're looking for 1, the value 1 in this tree, we can go 5. And then we know 1 is less than 5, so we take a left. We know 1 is less than 3, so we take a left. We know 1 is less than 2, so we take a left. But if it's equal to null, then it can't be in the tree. So then if we're looking for 4, 4 is less than 5, so we take a left. 4 is not less than 3, so we take a right. And then if we're looking for 6, 6 is greater than 5, so we take a right, so on and so forth. So that's how binary trees are kind of built up. And then to remove a node, yeah. To remove a node, we want to put a previous node to its head, basically, and then relinking everything up in order to keep the order, right? So we know everything to the left of the 2 would have to be, yeah. So we might do a delete or an insert in the binary search tree. Find mode, main media mode. Yeah, but there's an insert problem and a delete problem. We might do those next time, or we might do one of them tomorrow. I think that's gonna be all for today. I gotta take the puppy out one more time. And but y'all stay blessed, stay healthy. And we're gonna do the end queens problem eventually. I just don't think I'm up for the task right now as well. I'd probably look at the solutions tab and try to make sense of the code. But other than that, I wouldn't be able to take a head leap into it. So yeah. I don't mind that I stayed at this guy's house against my own will. That is false. This guy is tripping. But y'all have a good one. Y'all stay blessed and keep coding. Hey Devs is out.